Hello! So if you remember in the last few videos we've been trying to kind of come up with some way, some model of kind of trying to describe how things move. We've kind of tried to model random movement effectively. And if you remember right at the very start, we started off with a case where, you know, we started off in some position and we called that position 0, okay? Then with each time second that went past, so with each second that went past, we can either move to the left or right, but crucially, we can only move to the left or to the right by the same amount, so by equal time steps. We can move to the right or we can move to the left with each time second that goes past. Okay, so take one step to the right or one step to the left, and they're equal time steps, and that's it. So that was the first model that we looked at. Okay, and that was called the simple random walk, and we considered how that kind of, you know, as we considered how we took the discrete case, so kind of discrete steps, definite steps, into kind of continuous case, and I kind of likened that to discrete cases when we're kind of walking. Us as humans, we're walking along, we're taking discrete steps. Okay, whereas a snail, which is gliding along the ground, is a continuous steps, because if you like, it's just continuously gliding or hovering along the ground. Okay, so yeah, that was the first thing we looked at. Then the last video, we were kind of improving on that model. We're basically saying, actually, do you know what? With each second that goes past, we can move to the right and we can move by the left. But we can move to the right and left by any amounts that we like. So, for example, we could take a step to the right, or we could take a step to the left, and we could take a step by any amount that we like. So we could take a step more to the left or more to the right. Doesn't matter. And we also introduced this new thing where we could actually stay where we are as well. Okay, so that's kind of what we started with last time. As you know, that's what we were doing in the last videos. And we looked at kind of the probability that we would end up in a particular position after so many, you know, seconds have passed, effectively. Okay, and, you know, when we were considering the case where we could move to the left or right by any amount that we want, or we could stay where we were, we basically reduced it down to something what was known as the, well, it was called, I don't think I called it anything. It's actually called the drift diffusion equation. Drift diffusion equation. I know I talked about the diffusion or heat equation very briefly, but yeah, effectively it was this thing. So it's the partial derivative of P with respect to time. Remember that P was just a probability based on a position after a particular time. Yeah, so it's this thing. So, you know, what is the probability that we will end up at this particular point after, say, like 5 seconds? Okay, that's all P was talking about. Okay, and that was equal to minus U, which remember was a new variable that we introduced that was based on a limit of kind of, you know, position and time, and things like that, and so kind of step size and things, times by the partial derivative of my probability with respect to my position, okay, plus something called D, which is, if you remember again, a limit. It was actually called the diffusion. It's actually the diffusion. It's kind of how quickly things spread out. So in other words, how quickly we move away from a certain point, okay, and that's what diffusion is effectively saying. Again, it's just the limit of position and each time step, times by the second derivative of my P, my probability, with respect to X. Okay, and this was something called the drift diffusion equation. Okay, I talked about diffusion equation. I'll talk about that in just a moment. But the drift diffusion equation, this term here is what's known as the drift. Okay, this is what's known as the drift. It's sometimes called the advection diffusion equation. Advection diffusion instead of drift. But basically, the first term on this term here is the drift, okay? Because it's kind of it kind of takes into account that one direction might be more likely than the other. So, for example, if you start at a particular point, here might be food, and here might be no food. Well, fairly obviously, if you start here, then you're more likely to move to the right. So therefore, this drift term kind of takes into account that you're more likely to turn to the right. Okay. You're more likely to head towards the food or move towards in one direction than the other. Okay, and this second term represents diffusion. Which takes into account of kind of how quickly something spreads out. So you start in a central position, how quickly do you move away from that particular position? Okay, and that's called this drift diffusion equation, and that's what we came up with. Okay, and I said to you before that, okay, let's suppose that we take equal size steps. So in other words, right is R is right and L is left. So let's suppose that, you know, we take equal size steps to the right and left. Okay, so therefore, you know, if you take so therefore it becomes a half. You know, we dealt with that in the first few videos. So if right becomes left, then basically what we end up with is something known as the diffusion equation or the heat equation. Okay, so dB by dt effectively this term just disappears because you're not more likely to head in one direction than the other, because if r is equal to L, that's basically saying that you're taking equal sized steps. You know, you're moving in the right direction just as much as you're moving in the left direction. Okay, so therefore there is no drift. You're not more likely to travel in one direction over the other, so therefore there's no drift term. Okay, and that is just the case where d2p by dx squared, okay, and that is what's known as the heat equation, or just the diffusion equation, okay, and that is a partial differential equation. Okay, so what we're going to do in this video is we're effectively going to try and come up with a solution, more specifically to this thing, this kind of special case of this thing. I mean, we're going to talk about this later on, but it makes sense that, you know, if we can reduce this down and find a solution to that, then that might help us. That may well help us find a solution to this whole thing. Yeah. So basically, we're just going to consider this first of all and try and find a solution to this. Now, the thing is, I can go through all the PDEs and kind of the methods of PDEs and stuff, but to be honest with you, it's gonna cause more hassle than it's worth, quite frankly. So we're going to introduce some kind of new, kind of nice techniques, things to do with Dirac delta functions and things like that in this video, and try and basically derive a solution to this. So in other words, try and find out what P is. Hello. Okay. So in this video, I want to. Okay, so basically to try and solve this thing directly, if we wanted to try and solve this thing directly, we needed some initial conditions. Now, normally the initial conditions are, you know, the initial conditions kind of when we were considering it was that at t equals 0, we started at position 0. So this is position, you know, this is x is my position. So when t equals 0, you know, I start at this position here. So in other words, you know, I've got the initial conditions that t equals 0, then x equals 0, okay? But that may not necessarily be true. You know, I've just kind of, the way that I introduced this thing was basically saying, let's suppose that I start at some point, and I'm just going to call that point 0, and that's at the start of everything. But I could equally have started over here, or I could have started over here, or even over here, or, you know, 3 miles to the right, for example. Yeah, I don't know where I start. So basically, what I'm going to have to do is I have to introduce some special function. Now, strictly speaking, this isn't a true function. It's kind of more of a fudge function, I suppose. It's a function that I can use to get what I want, and it kind of replaces these initial conditions. You know, so it replaces the fact that I don't actually know where I start. Yeah. So try and find a solution to my diffusion equation. So, and it's called something called the Dirac delta function. Dirac delta function. Now, essentially, like I say, this isn't really, strictly speaking, a true function, but it's an incredibly useful idea. It's more of a fudge function. Okay, I like the word fudge, because sometimes mathematicians get kind of so obsessed about things that, you know, they're just effectively just making it up now, aren't they? You know. Okay, so here we go. So the whole idea is that basically it's a PDF, a probability density function. So in other words, it's a function that is defined by probability. So therefore, the area underneath that function, you know, if I had a function look like that, then the area underneath that function. The area underneath that function would correspond to my probability, and of course the total probability must be 1, so the total area underneath that function must be 1. Okay, so I'm going to use that kind of idea. So say, for example, if it's only defined from there to there, let me try and draw it out a little bit more properly. If it's only defined from there to there and 0 everywhere else, then therefore everything can happen in my situation must be defined by the area underneath that graph. So that's kind of the whole idea behind a probability density function. So what a Dirac delta function basically does is it's at the point x equals 0, so this is x along here. So at the point x equals 0, basically what I assume is I use that kind of idea, okay, but instead of it kind of being looking like a general kind of curve, a general kind of function, what I suppose is that at the point x equals 0, okay, I have an infinitely sharp peak. Oops, over my hand. An infinitely sharp peak. So in other words, it keeps going off to infinity. Okay, at the point x equals 0. Now, what is the width of that peak? It's 0. So in other words, it has a width of 0. Okay, but the height of it is equal to infinity. So it's an infinitely high peak. Well, that basically means that if I could take the area underneath that, okay, because, you know, okay, although the width is 0, yeah, the height is infinity, so therefore it kind of makes sense that the area underneath it is 1. Okay, the area underneath it is uncertainty. Now, obviously, I can't draw that. So basically, this line effectively represents the area. It effectively represents 1. Okay, so the area is equal to 1 because the height is infinite. Although the width is 0, the height is infinite. So therefore, the area underneath it, I suppose I should put area in brackets because it's not strictly speaking an area. Basically, that line represents everything that can happen in my function, okay? And it's only there at x equals 0. Everywhere else I've got 0. So effectively, the Dirac delta function basically says that I've got an infinitely sharp peak at the point x equals 0. So in other words, my PDF is represented there. Now, there's a special notation. There's a special notation for this Dirac delta function, okay? And it's it's a bit strange. It's basically a Dirac delta function. So a Dirac delta function, so D is for Dirac, and the delta is for the Dirac delta part, okay? And it's a Dirac delta function in terms of my variable x. So this is my notation for my Dirac delta function, okay? So in other words, I can use this initial condition, this function. I can use this function to define now an initial condition, because remember, what do I want? Well, I want P of xt. So in other words, I want values in here. Okay? Well, I know that at t equals 0, I will be at some point x. So, I mean, although I've defined the point x equals 0, that's kind of as a habit. Really, this can be any point. This is just my initial starting point. So wherever I start, this is what's going to happen. Basically, this is how I'm going to represent it. So at the point time equals 0, I'm basically going to get my Dirac delta function. So this is basically my initial conditions. Okay, now remember why I need to find these initial conditions, because I need initial conditions in order to try and solve this. I need some initial conditions. In order to try and solve it exactly, I need these initial conditions. So that's why I've set up this whole Dirac delta function. And this is effectively the governing equation of the simple random walk process, which we've discussed kind of in previous videos. Okay? Now, what do we know as well from other previous videos? Well, look, in other previous videos, we've found that our p of xt, so our probability function is it's not strictly speaking a function. It's kind of more probability, but in this instance, it's more appropriate to consider it as a function. I think I talked about that very briefly in the last video, and we defined it as this. So it was 1 over the square root of 4 pi dt. D is just our diffusion, okay? E to the power of minus x squared over 4 dt. Okay, so this is my probability. This is my probability function. This is how I defined it. It's like my PDF. Yeah, it came from kind of normal distribution. When I was considering my normal, simple random walk, and when I was going from discrete to continuous case, I was going from binomial to normal. I was going from binomial to normal. Binomial was my discrete case, and normal was my normal was my continuous case, and it was defined by this PDF. Okay, so basically the idea is, okay, we've got the initial conditions, and we've got what p is equal to. So now we can try and work out if it satisfies this thing. So dp by dt equals d lots of the second derivative of p with respect to x, or x squared. So this is basically my heat equation. So in other words, what I need to do is I need to find the first derivative of that with respect to t, and then the second derivative of that with respect to x. So in other words, I need to find that, and I need to find that in order to try and find, in order to try and find the solution to my, in order to try and satisfy my differential equation. So basically, what I need to do is I need to show that this thing in here, in fact, satisfies my initial condition. So it satisfies my initial condition. Actually, no. The first thing I need to do is I need to show that this thing satisfies that thing. So that's the first thing I need to do. Then what I need to do is I need to show that that actually satisfies that. So in other words, what I need to do is I need to show that this is actually a solution to that this is actually a solution to my diffusion equation, okay? Then if it is, then I need to show that it does in fact satisfy my initial conditions, and then I've got my exact equation. So those are two things which I need to do. Let me just write those. So the first thing I need to do is I need to show that actually this thing here does actually satisfy this equation. does actually satisfy my heat equation, my diffusion equation. What do I mean by that? Basically, I need to say that this is actually a solution to that. So in other words, when I plug this, so I find the first derivative with respect to t, then I find the second derivative with respect to x, and plug it in there, okay, that I show that the left-hand side is equal to the right-hand side. So in other words, this equation is in fact a solution. So that's the first thing I need to do. And if I've shown that, then I need to show that my solution, what is effectively going to become my solution to my heat diffusion equation, I need to show that it does in fact satisfy some initial condition, and the initial condition which I've defined is via my Dirac delta function. Okay, so let's go about trying to show that that satisfies that. So what do I need to do in order to do that? Well, I need to differentiate this thing with respect to t, okay, then I need to differentiate this thing twice with respect to x, okay. So this could get a little bit awkward. It's just basically algebra, okay, and the way which I'm going to do it is basically just by rewriting it. So I'm going to try and rewrite this thing, and first thing I'm going to try and do is just find the derivative of p with respect to t, okay. So basically I want to try and find the derivative with respect to p. Well, this is actually, as it is, it's quite difficult, because to try and find the derivative of that with respect to t, that looks quite nasty. It looks like quite a nasty thing, so I'm going to have to use product rule by the looks of things and chain rule all in one, and then I'm going to have to try and, you know, use again the chain rule with that, and maybe a bit of substitution as well. So it's going to get quite nasty, but I can make it a whole lot easier for myself by basically just taking logs of both sides. So if I take logs of both sides, watch this. So I'm going to take the natural logarithm of p. So now I'm just going to call p of xt like I did over here to make it easier to deal with. I'm just going to call p of xt just p, okay? So log p is going to be equal to the log of all this thing. So the log of 1 over square root of 4 pi dt, okay, times e to the minus x squared 4 dt. Okay, so I'm just taking logs of both those things. Oops, taking logs of both those things, right? So now what I'm just going to do is, just by laws of logs, if I've got two things being multiplied together, so I've got a log of two things being multiplied together, that's the same as log of that thing added to the log of that thing. So that's effectively how I'm going to break this up now. So this is going to be log of 1 over square root of 4 pi dt, okay, log of that, plus log of e to the minus x squared over 4 dt, okay. So I've broken those logs up. Well, look what I have here. Now, I don't know whether you remember this. It's dead easy to show. Basically, if I have the natural logarithm of let's say e to the power of something, so e to the power of a, let's say, and I'm going to basically call that b. I'm going to call that b. So therefore what I'm just going to do is I'm just going to rewrite this. I'm just going to rewrite this in such a way. So what this is saying is log to the base e is of that thing is, what am I trying to say? I'm basically saying e to the power of what equals that thing. E to the power of what equals that thing. So basically I'm just going to rewrite this using my, using logs, the whole point of rewriting logs. If you have e to the power, so if you have 2 to the power of 3 equals 8, then I can rewrite this thing into anything I should want. So if I want to write the 3 as the subject, so 3 is equal to log to the base 2 of 8. Okay, so log to the base 2 of 8. So effectively this is what I'm going to do here, but here my base is e. So basically what I'm going to do is I'm going to say e to the power of b equals that thing in there. Equals that thing in there. So e to the power of a, is that right? Yeah? I always ask myself the question when I have logs like this. I basically say e to the power of what equals e to the a. Okay, and that's what the what in that question is b. Okay, so that's kind of what's going on here. So basically I'm showing that e to the power of b equals e to the power of a. So therefore, are you happy that these two powers must just be the same? So therefore what I'm saying there is b is just equal to a. Well, look what b was equal to in the first place. B was equal to this thing. So now I can just replace b here by a. I can just replace b here by a. So in other words, when I have log of e of something, then that something can just be written on its own. So in other words, the log and the e just kind of cancel each other out. And I'm just left with a. So if that made some sense to you, good. It can kind of be seen by the verse process, but I think I've kind of made it clear. So look, that's exactly what I've got here. I've got log of e of something. So therefore I can just, the logs and the e's kind of cancel each other out, and I'm just left with that something. So let's just try and make that a little bit bigger. Just left with something, make it a little bit bigger. So therefore I've got minus x squared over 4dt. Over 4dt. So that's what I'm left with now. So I'm just going to replace, I've got a plus and a minus there, so therefore I'm just going to be left with a minus, okay? So this is what I'm left with. So log p is equal to that thing, okay? And I'm just going to write it such that, okay, and I'm just going to I'm just going to use this actually. I'm going to rewrite this. So this is effectively, are you happy that I can rewrite this thing inside the brackets, if you like, as 4 pi dt, okay, raised to the minus a half, okay? That is effectively what that is in there, yeah? It's 4 dt raised to the power of minus a half. Well, by log laws, I can just take this minus a half and stick it out the front. I can take this minus a half and stick it out the front, okay? So this is effectively what I'm left with, right? So I'm left with this. This is what I'm going to work with, okay? And I'm going to take the derivative of this. Oops. I'm going to take the derivative of this. So, sorry, the derivative with respect to t of ln p, because that's what I'm after. I'm after trying to find what ln p, dp by dt is. Okay, so ln p by dt. So this is going to be equal to the derivative of all of this thing. The derivative of all of this thing. So this is minus a half ln of 4 pi dt minus x squared over 4 dt. Okay, oops, 4 dt, and I'm going to try and take the derivative of that thing. So, what's the derivative of the natural logarithm of p? What's the derivative of the natural logarithm of p? This is going to be, what's it going to be? This is just going to be the chain rule, right? It's just going to be the chain rule, because basically what I can do here is I can use a chain rule to basically say, well, okay, what I want to do is I want to find the derivative of the log of p with respect to t. Okay, well, therefore, I can't at the moment do this because, I can't take the derivative of the log of p because there's no p, there's no t in the log of p. So, I realise I'm just shouting letters at you now. But, effectively, if you want to take the derivative of y with respect to x, if I want to take the derivative of y with respect to x, then basically I need y equals something on the right hand side which involves x, something on the right hand side which involves x. So here I want to take the derivative, of p. Well, I can't take the derivative of p with respect to t because there's no t in this log p. You can't see a t inside that log p. But I can break it up into the derivative of log p, okay, and I have, just by chain rule, I'm going to multiply that by something where I have the derivative of t on the bottom, okay, but as long as that thing is the same as that thing, then those two things will just cancel and I'm just left with that again, okay, so this is just all the chain rule is saying. So what do I actually want to differentiate with respect to? Well, this has got a p in, log p has got a p in, so therefore if I differentiate with respect to p and stick a differentiate with respect to p up there, those things will just cancel and I'll just be left with this thing on the right anyway, okay, but actually I can use this because I can say, well, what is the derivative of log p with respect to p? It's just 1 over p. What is the derivative? What's the derivative of log p? Okay, it's just going to be 1 over p. It's going to be 1 over p. Okay, so therefore I can just replace this thing in here with 1 over p. Okay, but I'm going to have to multiply it by dp by dt. By dp by dt. So in other words, I can replace this thing here by that thing there. Okay, so hopefully that makes a bit of sense. So I'm left with, if I just replace it like this, so 1 over p times the derivative of p with respect to t. That's the whole idea there. Okay, cool. So now I need to look at this right-hand side. Well, let's have a look at this right-hand side, shall we? Let's have a look at this right-hand side. Well, I want to differentiate. I want to differentiate with respect to t. I want to differentiate with respect to t. So in other words, anything which isn't a t inside this, so I want to differentiate all this with respect to t. Anything which isn't a t inside this bracket, effectively, I'm not interested in. I'm just going to treat it as a constant. So in other words, I want to try and isolate t's on their own. So I'm going to actually isolate this t here. There was a t there. So I'm just going to isolate this t here by saying this is just multiplied by 1 over t. That's the same thing. So effectively, I can just treat that as a constant. Okay, I can just treat that as a constant. Likewise, I can use log laws in here. Because remember what I used the log laws up here? I used a log law up here that I had, the log of something times another thing. It's just the log of that first thing plus the log of that second thing. So I can use exactly the same thing here by breaking this log of 4 pi dt up, this log of 4 pi dt up, into log of 4 pi dt up, into log of 4 pi times t. So log of 4 pi times t. So therefore, if I break it up into log of 4 pi plus log of t. So log of 4 pi t, sorry, log of 4 pi d plus plus log of t, log of t. Okay, so now, you know, and I've got to multiply through by minus a half, remember, so this is minus a half, and this is minus a half in here as well, minus a half log t. Okay, so now this makes it easy to differentiate with respect to t, because when I differentiate with respect to t, okay, when I differentiate that thing with respect to t, that's just going to be a constant, because I haven't got anything involving t in that term there. I haven't got anything involving t in that term there. So therefore, that's just going to become 0. It's just like differentiating a constant. That's easy. Okay, this is going to be, it's exactly the same thing as I had before. It's just the derivative of a log of something. It's just 1 over that something. Okay, so it's going to be minus a half, that's just a constant, times by 1 over t. Times by 1 over t. So let's just combine those two things together. I end up with 1 over 2t. 1 over 2t. Cool. Okay, so that's kind of that's quite happy. I'm quite happy with that. Okay, and then this thing with respect differentiated with respect to t. Well, this is just a constant, so that just comes along for the right. So I end up with minus x squared over 4d. Okay, times by the derivative of derivative with respect to t of 1 over t. Well, this is just like saying, you know, this is just like saying t to the minus 1. So what's the derivative of t to the minus 1? It's going to become minus t to the minus 2. Minus t to the minus 2. So that's what that is. Okay, and I could just write this as, you know, this times that. So I've got a minus there, so therefore that becomes a plus. That becomes a plus, okay? And I can rewrite this as 1 over t squared. 1 over t squared. So I'm just going to put it all back together again. And I'll end up with, in here, this is just going to become 1, you know, just put t squared in there. Okay, so hopefully, you know, if you follow that, so in other words, what have I got? I've got 1 over p dp by dt, okay, is equal to that thing. Well, I don't want 1 over p dp by dt. I just want dp by dt on its own. So I'm going to have to multiply through by p. Multiply through by p. So if I multiply that by p, okay, then what do I end up with? I just end up with that. So now I've got the first thing in my differential equation. Okay. Now what do I want? Well, I want my second derivative of p with respect to x squared. I want my second derivative of p with respect to x squared. Okay, so I want d2p. I want d2p with respect to dx squared. Let me just write out what p was again. Or rather, let me just write out what I had here. So what I had here, you know, because you're happy that I can just use that. I can just use that same technique. So I've basically just rearranged that to get that. Okay, so I'll just rewrite this out again for you. So, okay, I've written it all out again. So I'm after this. I'm after d2p by dt. I've got this, okay, and I want to find out what that is. I want to find out what d2p by dx squared is. Okay, so how I'm going to do it is I'm going to differentiate with respect to x first. So I need to, you know, first of all, I need to find dp by dx, okay, and then I'm going to differentiate that whole thing with respect to x again. So once I've found that, I'm going to differentiate it with respect to x again to find what it is. So let's find out what dp by dx is. Okay, well, basically what I'm going to have to do is I'm going to have to differentiate all of this thing by dx. Okay, so I'll have to differentiate with respect to x of natural logarithm of p. Okay, same thing as before. Equals derivative with respect to x of minus a half natural logarithm of 4 pi dt minus x squared over 4 dt. Okay, and I'm going to have to differentiate all of that with respect to x. Okay, so let's have a look at this. Well, if I differentiate this thing, I can use the product rule again. I can use the chain rule again. So I want to differentiate this thing. So I want derivative of ln p with respect to x. Well, there's no x inside that ln p, so in other words, I'm going to have to introduce I'm going to have to use the product rule. Sorry, not product rule. I keep saying product rule. It's chain rule. Okay, so I want the derivative of ln p here. I want that multiplied by some fraction where the derivative of x is on the bottom. Multiply the two things. And I want the same thing here. So I've got a p in here. So let's put a p on here. So dp here. Okay. So what's the derivative of ln p with respect to p? It's just going to be 1 over p. It's going to be 1 over p. So therefore, this is what I'm left with now. So this is this left-hand side. So this, which is what I've got there. Okay. Those two things are the same. So I can just replace this thing with that thing there. Okay, just place those two things together. So what have I got? I've got 1 over p times dp by dx. Okay, so that's the left-hand side sorted with. And, of course, I can just multiply through by p at the end if I want to, which I will do. Now I need to look at this thing. So I want to differentiate all of that thing with respect to x. Well, that's quite straightforward. Because look at this first term. This minus a half ln of 4 pi dt. That hasn't got an x in. That has not got an x in. So that term is effectively just a constant. Because if it hasn't got an x in, I'm just treating it as a constant. Yeah? Or if it hasn't got an x, if it's not an x, it's a constant. Okay, providing it's not like a ln or e or ln or anything like that. Plus, minus, whatever. If it's so in other words, the 4 pi d and t are all constants. So therefore, the derivative of a constant is just going to be 0. Oops, just going to be 0. I didn't mean to do that. Although actually I did. Sorry. So the derivative of that thing is just going to be 0. So therefore, I'm just left with the derivative with respect to x of that thing there. So therefore, if I just isolate this a little bit, so in other words, this is just x squared times by 1 over 4 dt. So it's just times by that. So therefore, this is just a constant, so it comes along for the ride. So in other words, this is just 1 over 4 dt. Okay, and then I just have to differentiate that thing. So the derivative of that thing is going to become minus 2x. Minus 2x. So if I multiply minus 2x by that thing now, what am I left with? I'll be left with minus 2x over 4 dt. Minus 4x over 4 dt. Okay, and remember I want dp by dx. I want dp by dx because then I can differentiate that thing again. So at the moment this is 1 over p times dp by dx. It's easy enough. Just multiply through by p. So I've got this multiplied by p. Okay, so this is what I've got here. Okay, but remember I want d2p by dx squared. So in other words, I'm going to have to differentiate this thing again. So if I differentiate this thing again with respect to x, okay, that's going to be the derivative of that thing with respect to x. It's going to be minus 2x over 4 dt times p. Okay, so differentiate that thing again with respect to x. So what do I end up with? Okay, well, first things first, I'm just going to isolate what I don't need. So I'm just going to treat the 2 over 4 dt, I'm just going to treat that as a constant. So I'm just going to write this as x times p over 2 4 dt. Okay, so this is my constant now, and I'm actually going to stick that constant out the front of my ddx. So let me just show you what. So this is what I mean now. So I've just written this, which is just a constant, outside that. Now, why have I written it like that? Because you may be saying, well, p's not a constant, is it? P's not a constant. Remember that p is a function. Remember what p is? P is a function involving x. P is a function which involves x. So therefore, if I want to take the derivative of, I can find the derivative of x, that's fine. But the reason why I've kept p in there is because p is a function involving x. So therefore, I've got two functions which have x kind of in them, either written there, there's an x clearly written there, or there's an x which is hidden in there, in that p. Okay, so therefore, I'm going to have to use, because I've got two functions involving x, being multiplied together, so therefore I'm going to have to use something called the product rule. Okay? So let's have a look. And see what it is. The product rule is dead easy. It's going to be the derivative of the first thing multiplied by the second thing left alone, plus the other way around, the derivative of the second thing multiplied by the first thing left alone. Okay, so let's have a look. So I'm just going to leave the minus 2 over 4 dt out the front because that's just going to be a constant. Okay, that will be multiplied by the derivative of x with respect, so derivative of x first, which is going to be 1, okay, times p, yep, 1 times p, plus then the derivative of p multiplied by x left alone. So I'm going to leave the x there, and I then want the derivative of p with respect to x. Right? So that's what I end up with just by the product rule. So maybe if we just get rid of that 1. Well, what is the derivative of p with respect to x? The derivative of p with respect to x is that thing there. Derivative of p with respect to x, I've just worked it out as that thing there, so I can just make a straight substitution. So therefore, this is equal to minus 2 over 4 dt multiplied by p plus x lots of, just substitute that for that, okay, so I end up with minus 2x over 4 dt, times p, okay, and that's what I end up with. So let's just do a little bit of simplification. That doesn't look quite like a d. There we go. So there we go. Let's just try and do a little bit of simplification now. So I end up with this. So just expand out the brackets first of all. So I end up with minus 2 over 4 dt. Okay, lots of p plus, well, this is now going to become a minus x squared, yeah? Minus x squared, minus 2x squared times over 4 dt. That's going to be multiplied by p, okay? I'm actually just going to take a p out. I'm just going to take a p out, so let's just factor out p straight away. One there, okay? And then let's multiply through by that. Let's multiply through by that. So what do I end up with? I end up with, if I multiply through by that, I end up with this multiplied by that, so I end up with minus 2 over 4 dt, okay? Multiplied by this. Now, if I just write this x squared here, and if I multiply this by the same thing, you're happy that's just going to become squared? Because I'm multiplying through by minus 2, and if I stick a minus there, that's going to stick a minus there. Effectively, all I've just done is I've just multiplied that thing there by 2 over 4 dt. 2 over 4 dt, okay? I'll just raise it to power 2. I mean, if you do it yourself, you can see that quite easily, but hopefully you kind of follow the logic there. So that is equal then to minus, what's that equal to? Well, actually, I can just do it using my, because I've got the luxury of being able to raise things. I've got 2 there and a 4 there. They will cancel to 1 over 2. They will cancel to 1 over 2. Okay. Again, I've got 2 there and I've got 4 there, so they'll cancel to 1 over 2. So let's try and square this thing out now. So what's minus 1 squared? What's minus 1 squared? That's going to become 1. Okay, so I'm squaring this thing out. Okay, then the bottom, this 2 is going to go to 4, this d is going to go to d squared, and this t is going to go to t squared. So effectively what I end up with is this thing here, so x squared. Let me just write it around the other way to make it look a little bit neater. X squared over 4 d squared t squared, d squared t squared, minus 1 over 2 dt. Okay, and that's all multiplied by p. That's all multiplied by p. So now I know that d, this is d of dx of dp by dt, dx. Again, just treat it like a fraction. How many dx have I got multiplied together? I've got 2, so multiplied by itself. That's dx squared. Then I've got how many d's have I got together? I've got d squared, so d squared. So this is what my second thing is. So what do I end up with? What do I end up with? Well, so these are the 2 things which I've just worked out now. I've just worked out those 2 things. Remember what I want to show. I want to basically show that the derivative of p with respect to t is equal to d lots of the second derivative of p with respect to x squared. This is my diffusion equation. This is what I want to satisfy. So in other words, when I put that in there and that in there, the left-hand side is equal to the right-hand side. Well, is it? Well, let's have a look. So let me just write, this is the left-hand side. So it's minus 1 over 2t plus x squared over 4 dt squared times p, and that must be equal to d lots of this thing here. So this thing here. So this is my right hand side. So it's d lots of minus 1 over 2 dt plus x squared over 4 d squared t squared times p. Okay, well, if I multiply through by d, what do I end up with? I end up with d here and a d here. That d will cancel with one of those d's here. Oh, what was there? That was an x squared there. And that d will cancel with that d there, so just leave a 1 on the top. So therefore, the left-hand side is equal to the right-hand side. So therefore, my solution, my equation, my p equals 1 over square root of 4 pi dt, e to the minus x squared over 4 dt, that does indeed satisfy this diffusion equation. So therefore this is a solution. So I've shown my first part, which I wanted to show. I've shown that this is in fact a solution to there. Now of course, if you work through the algebra yourself, you'll actually realise it's not that bad. The little trick which you had to make was just taking the natural logarithms. But I mean, it wasn't that bad. This is all you have to do. You basically have to just show that satisfies that by just kind of taking by taking the derivatives. Okay, the next thing which we need to go on and then show that it satisfies the initial conditions, which is going to be in the next